This is an instructional video for the deconvolution-based spontaneous postsynaptic current detection method developed in the Peter Jonas lab, but developed inside MIES, a software program that's based in Igor Pro. And this is the paper that the detection method is entirely based on. So here in Igor Pro, we can load some data using the analysis browser, some previously recorded experimental data. I've already found this file, so I just got to load the sweeps at this point. And now let's visualize the data we're going to need to analyze it, or at least the components of it that we want to have eyes on. So let's visualize the epochs. So here we go. We can see that this is the DA trace, and here are the epochs. If you hover over it, you can see the name of the epochs. So the epochs are just, how the data is divided up in time. So you can see here there's a test pulse inserted into the data, and then here are the test pulse epochs: TP baseline 0, TP pulse, and TP baseline 1. But we're interested in the non-TP data, so we're going to be interested in analyzing this epoch 0 data here. So we can go to the sweep formula tab. So this sweep formula contains a number of high-level operations for analyzing electrophysiology time series data. I've got a formula already staged in my copy and paste that I'll walk through, in my clipboard that I'll walk through. So here we're going to select the data we want to work on. So we define a variable called select in this case, and we use the select operation to gather data from channel 89. So that's this channel here that has the acquired data on it. We're going to do this work on analyze these sweeps, and this all operation says include these sweeps whether or not they're displayed here. We're going to use epoch 0, so we're defining our epoch with its short name, epoch 0. Recall that's the name shown here. And now we're going to define our kernel. So that's the kernel that's used for the deconvolution, and basically what you're doing is making a guess about the rise time and the decay and the amplitude of your kernel. And you can do that in Igor pretty easily by taking a look at some of your events and looking at how long they take to rise and decay. And of course this is Igor, so it's pretty trivial if you want to do quick fit to measure a decay. So let's do that. And oops, sorry. And let's do a quick fit. And let's do an exponential x offset. And then the results are printed in the history window down here, and we can see the tau is around 0.36 milliseconds. Anyways, if you can do this for a number of them, you can guess it. I made an initial guess for the decay tau of 1 and the rise tau of 0.45 for your kernel. All right, so once you've defined your kernel, you need to define a detection threshold, and the way that's done in the Jonas paper is by doing an all points histogram of every point in every sweep, fitting that with a Gaussian, and determining at what level. So that's an all point histogram of the deconvolved trace, determining a standard deviation level that you'll that will set your detection threshold. So here we're going to use a standard deviation of 2.5. Again, that's a standard deviation based on the Gaussian fit to the all points histogram. And now here's our PSX operation. We need to name this analysis we're doing, so I just chose quack for the fun of it. We're going to use our kernel. we're going to define our number of standard deviations, and we're going to define our filters, our high and low pass filters for the deconvolved trace. And then we would run it, this operation, and then we're going to do plot some of the plots that will help us do some quality control and ultimately some analysis, look at the statistics of our minis. All right, so now that we've got this in here, let's display it. And this opens up the sweep formula window. It's a specialized window for the PSX operations. In this case, it has this upper window, which is showing you all the individual events, either overlaid or one at a time. And here's your window that displays the time series from each region you defined in your select operation. So basically, in this case, there's one for each sweep, and it shows you which epoch, and it shows you all the detected events. Now that events can be classified in three ways: as undetermined, accepted, or rejected events. And they all initially are classified as undetermined. So we need to pass or fail these events. So one way I think to do that, rather than, you can of course look at every event and go through it using the keyboard shortcuts, which are the instructions for those are shown here in the UI. You just hover over that UI button and it shows you all the keyboard shortcuts. So you can use the arrow keys to go between events, left and right, and the up-down arrow keys to pass or fail an event. And after you've passed it, it jumps to the next event or failed it. So there, I went back, and now you can see that this event is marked in a green circle to indicate that we passed this event. And so this is plotting all the individual events up here. Now you can see we have one passed event, and it's showing you the event here plotted as well, the individual event. So you can see it in view, and you can also see the fit to the decay in a zoomed in view, and also see the fit to the decay. But of course, doing this one at a time is quite tedious. We can look at the amplitudes and know likely that these bigger events are going to be good. So we can select them. Let's do a threshold of, I don't know, around minus 10 picoamps. And let's select all these other events, right click, and go accept event and fit. This will automatically update and save that QC and update the plots. And now we're left with just the events that we might want to take a closer look at because they're sort of smaller events and they may actually be noise. So what we can do is we can place this cursor A on any event here. And now, again, using the arrow keys with this plot selected, we can look at all those events. So this one here clearly just looks like a noise. It doesn't look like a true event to me, so I'm going to fail it. Same for this one as well, and this one, and this one. This one, could be real, could not. This is, up to you. That rise time looks a little slow to me, so I'm going to fail it, and I'm going to fail this one as well. This one's got a nice fast rise time, so I'd pass it. All right, so just for the purposes of this demonstration, to speed things up, I'm just going to pass and fail a bunch of these, holding the arrow key down, and we'll walk through all these events, passing and failing them. Right now, I'm just passing a bunch by holding down the up arrow key. I'm holding the down arrow key, failing some. When it gets to the last event in the last range, it'll stop. But because we placed it on an event that wasn't necessarily the first event in the first range, we'll likely need to come back to this. So let's store those QC results. So we stored them. Let's display the updated plot. Right? Let's go back here and pass or fail the events. We didn't. Normally, you'd be looking at all these events individually, checking the fits, seeing if you like them. But just for speed, I'm going to quickly pass and fail some of these events. All right, we've got to the end of that one. Let's store, display. Probably need to do this one more time. Place the cursor on here again. And let's store those, display. All right, so now there's no more undetermined events for this data that we're analyzing. All right, because we're plotting the undetermined. Now, if we wanted to do this, we can also look at the accepted events. So let's plot the accepted events, their amplitudes. Do that here. And now we can see these are all the accepted events, their amplitudes. All right, so we've QC'd these events based on amplitudes, but we also want to check if the fit to the decay of the event is appropriate. So let's do this. Let's look at the taus, the decay tau for all the accepted events. Let's display it. All right, so now you can see that there are some really long taus here. The code does some tricks to like minimize getting these long taus, and the default is that the tau can't be 10 times longer than the duration of the time series used for the fit. But still, there's some cases where there's relatively large spaces between events, and so the amount of data used is reasonable, is reasonably long, and 10 times that can give these long time constants. So let's look at these and decide if they're good. So I can look at this right away and know that's a bad, maybe it looks like possibly a real event, but it's the fit's bad. So I'm going to use the Z shortcut key to reject. So you can see the status is up to here for the fit, but the event is still accepted. So let's look at some of these other ones. That one doesn't look so bad to me. The fit looks fine to the data, in my opinion. Here's another one where the fit looks fine. Let's look at this one. So basically, we're going through all these ones with the really long taus. Here you can see that I think the fit should have gone between here, and it didn't, so I'm going to reject that fit. Here's another one, a fit I'm going to reject. Again, another fit that, it should have been between here and here, but because there's no detected events after this, we sort of try to maximize the amount of data used within limits. So I'm going to reject that fit as well. You can see that the status has been updated here. The code limits the amount of time used for the fit based on either whether there's another event there, or it can't be more than 10 times longer than the decay tau you specified in the kernel. So I specified 1 milliseconds, so that means the time for the fit cannot be more than 10 milliseconds. All right, let's keep looking at these ones. Again, here there's like a second event that's making the fit poor, so let's do that. Let's fail that fit. Same story here. So yeah, so for these really long fits, it looks like they are for most of these really long fits, there's fits that she failed. So I failed them using the shortcut key, but recall you need to store those results now. And now if you display this again, you'll get an updated plot with those failed, because we're only plotting accepted taus, all those failed fits removed. Let's take a look, one more look at this long one. Oh yeah, that one also looks like one that should be failed. So, and let's take this, maybe look at this one here. That one looks okay. So let's store that last one, display one more time. All right, and so now some reason I'm Not sure why that one's persisting. Oh, there it goes. It's gone now. Okay. So now we're satisfied. We've done our amplitude quality control. We've done our decay fit quality control. So I think we're sort of happy with all with the QC at this point. So let's look at the statistics of the events we've detected. So first, this here controls the display of all the individual events overlaid, and you can display the accepted ones, the undetermined ones, the rejected ones. So let's just display one at a time for demonstration purposes. So here's all the rejected events that we pulled out. Here's all the accepted events. Right. But you can also display the average accepted event, for example. And you can do that based on event state or the fit state. So if you're going to use the fit, if you're going to use the parameters of the fit to extract time constants from the average, then I recommend using the fit state. So here's our fit to that using the double exponential peak, and you can get the values for this fit by hitting this button or hovering over it. You can see the fit results there. Hitting this button just puts the fit results into the clipboard. Okay, so this is your all event plotter where it plots them overlaid. Again, here, let me just show you a couple more bits of functionality, right? So let's say all the accepted events, that might be overwhelming to view them all at once. So you can change your block size. So we're showing all the data right now. Let's show 2% of the data in block 0. And now you can look at those, and then you can look at the next block and so on and so forth. So you can get sort of a close-in view of a more clear view of all your events overlaid if you wanted. But anyways, let's switch that block size back to 100% and now get all the events displayed again. All right, so here's your all event plotter and here's your individual event plotter. Again, that one is tied to what's going on in these plots. So as you go through events, that one updates and it displays the event on its own, its fit, and then the legend also tells you, the statistics of that individual event. All right, so now that we've done this, let's look at the statistics of the miniature events we've detected. All right, let's start with amplitude, and let's display the amplitude of the accepted events, and let's display it as a histogram. And let's do that with the other metrics we obtain for mini. So I'm going to just copy and paste that same one a few times and then just make a few small changes to it. So now we're doing amplitude. Let's look at the tau. Let's look at the rise time. And let's look at the interval between events, x int. And instead of displaying 4 plots, let's display those histograms all on one plot. All right, so let's look at those histograms. All right, so those are all the histograms. Right now, they're color coded by the head stage the data was obtained from. So we're using, 89, and so that's color coded in red, and that's why all these are red. In future versions, when the same head stage is used, we'll automatically change the color code. But for now, since this is Igor, it's pretty trivial. You click on it, you select some colors that you like, and now you can see the right. And so the ordering of those histograms is the order that's in the sweep formula window. So the first one is the amplitude. The second one in orange is the tau. The third one in green is the rise time, and the fourth one is the interval between events. All right, so that's histograms, but you can also do the same thing with statistics. You can also get out statistics. do that instead of doing the histogram as post-processing. Let's do stats for all those. This will make another plot with all those, the statistics of that. So let's do that. Our color coding will be lost, unfortunately, for now, but we can add it back relatively easily. So let's just add it back to make things clear for this demonstration. Let's do the same one on this one. There you go. All right, so now we're plotting the statistics of the amplitude, tau, decay tau, the rise time, and the x interval. And the rise time we're plotting here is the 20 to 80% rise time. That's the default rise time that we calculate, but you can actually parameterize your PSX operation to include other rise time thresholds. So like 1090 is another relatively common one. All right, so now you have all these results nicely plotted. You know, you can use that for a figure, what have you, but you may want to just get the results out of here and, you know, use them, analyze them in another program. So for that, I recommend using the store operation. So any result here you can wrap in the store operation. So you can, so I'll just do one example here. So let's do store. We're going to give this a name. Let's call this amp accepted. And then that's what we're storing. So we just got to put one more around there. Display. So nothing will change on here. It'll all look the same. But now this stores these values that are plotted in this histogram in JSON formatting in the results wave. So let's just quickly look at that. So let's go to MIES results. Let's look at the text results textual values array. And so we need to go to the last. So all sweep formula results are in the last layer of the results wave, and we can go, let's make this a little bigger so we can read them. And I'll know this will be in like the last column. So here it is, sweep formula store operation. We named it amplitude accepted, and there's the formatted JSON. So that's a little hard to read in a single cell. So maybe let's pull up, get that in a JSON editor. All right, so here's the raw data for that histogram. Here's other information that allows you to, like it's telling you what data was used for that analysis, and other information about how to plot this data in the same way it was plotted as Igor does it. All right, so you then use whatever program you want to parse this JSON data and use it, whether it be in Excel or Python or what have you. All right, so that's a quick instructional overview of the PSX operations of sweep formula inside MIES Igor for mini detection. Thanks very much.